Hi, this is Nat, and this is going to be your video lesson on calculating simple probabilities. We're also going to talk a little bit about simplifying fractions and finding equivalent fractions, which are both skills that will help you with probabilities, and also, among other things, help you understand why it is that solving proportions works the way it does. Some interesting qualities of fractions that we'll go over. So starting off here, let's talk about how you calculate probabilities. If you remember from our last lesson, a probability is a way of numerically expressing how likely something is to happen. And we can give it as a percent, decimal, or fraction, but for today we're going to really be focusing on fractions because that's the most intuitive way of creating probabilities. And we calculate a probability by taking the number of outcomes we're looking for and putting it over the total number of possible outcomes. Now we could fiddle with this equation a little bit and put our probability over 100, and that would give us our probability as a percent. But like I said, we're going to be working mostly with fractions, so we're not going to worry about that right now. The other thing that's worth talking about is what is an outcome? Well, an outcome is something that can happen, so it really depends on what kind of event you're trying to calculate the probability for. If I'm rolling a die, or a six-sided number cube, as textbooks like to call it, if I'm rolling a die, outcomes are the faces that can come up. So if I'm thinking about possible outcomes, there's 6 things that can happen if I roll a regular six-sided die. So the number of possible outcomes would be 6. The number of desired outcomes depends on what I'm trying to figure out. If I want to know the probability of rolling a 1, first of all, this is probability notation. The P with the parentheses, that means the probability of rolling a 1. Okay, if I'm trying to figure out the probability of rolling a 1, all that is the number of possible things that can happen, which is 6, because there's 6 sides on the die, and then the number of desired outcomes. In this case, I have to think how many 1s are there on the die. Well, that's 1. There's 1 1 on the die, so the probability is 1 in 6, meaning 1 out of every 6 times I roll a die, I would expect to get a 1. Now, don't get confused by the number 1 here. This is a really common mistake. People think, well, the 1 and 1/6 over here comes from the 1 here, and that's not true. The 1 on the die has nothing to do with the probability. It might as well have been an A or the color purple. If, for example, I change that 1 to a 2, the probability is still 1/6 because there are still 6 sides on the die, and there's still only 1 2. So the probability of rolling a 2 is 1/6. Let's say, on the other hand, that I am playing a game that involves this nifty little spinner with different colors on it. Again, I can figure out my probabilities pretty easily. The only thing I need to know is what I want the probability for and how many things can happen. Well, how many things can happen is going to be determined by the number of spaces in the spinner. And if we assume they're all equal, there's 1, 2, 3, 4, 5, 6, 7, 8 things that can happen. A common mistake is to count the colors and think, okay, there's yellow, that's 1, there's purple, there's green, there's orange, and there's pink. So there's 5 things that can happen. This is not true. There's 8 spaces, so there's 8 things that can happen. So if I, for example, want the probability of spinning purple, well, that's going to be equal to the number of purple spaces, which is 1, over the number of things that can happen, which is 8. So I have a 1/8 probability of spinning purple. 1 out of every 8 times I would expect to spin a purple. My probability of spinning yellow, on the other hand, is different, because there's more yellow than there is of anything else. So I'd expect it to be more likely that I would spin yellow than, say, purple. So the probability of yellow is going to be the number of outcomes that are yellow, and that's 3. 3 of the spaces are yellow. And there are still 8 things that could happen, so the probability of yellow is 3/8. And that's how you calculate simple probabilities. We could pretty much stop there, but let's do one more as a segue into our next idea. Let's say that I have this bag of marbles, and it contains 4 blue marbles, 5 purple marbles, and 1 green marble. Well, one thing that I could calculate here is the probability of pulling a blue marble. So the probability of pulling blue is going to be the number of blues out of the number of marbles. So in this case, 4 blues out of a total of 10 marbles. My probability could be expressed as 4/10. That, though, gets us into this important idea of simplifying fractions. The value 4/10 definitely represents my probability accurately, but it's not as simple as my probability could be. What this means is for every 10 times I do something, I'd expect to get blue 4 times, or every 10 times I pulled a marble, I would expect to get blue 4 times. But whenever possible, we want to simplify fractions so that they account for smaller numbers of outcomes or smaller numbers of times we would do something. So 4/10 best represents the idea that if I did something 10 times, it would happen 4. The simpler fraction 2/5, though, is better because now I've reduced the whole thing and it's easier to understand. It probably is easier to apply now to other situations. So for every 5 times I draw a marble, 2 should be blue, is a little simpler than for every 10 times 4 should be blue. And simplifying, if you have trouble remembering how it works for a couple reasons. If we want to, we could think of it in terms of pictures and these fraction bars here. You can see that where I've represented 4 out of 10, the 4 out of 10 takes up an equal amount of space as 2 out of 5 on the same length bar. The reason being that I've functionally just taken these extra divisions, every other division between bar, and eliminated it so that it's the same now. I've functionally divided the number of bars in half, which is more or less what I can do with the fraction itself. The way I really like to explain simplifying fractions, though, is that we're really eliminating common factors. Any number can be represented by 2 other numbers multiplied together. Let me show you what I mean. 4, if you look up here at my fraction 4/10, is really just like 2 times 2. And 10 is really like 2 times 5. Well, in a fraction, anytime I see 2 numbers that are the same, so in this case I can see that there's a 2 and a 2, those are common factors. And it's always okay to eliminate common factors in the numerators and denominators. So if I remove these, I get to my simplified fraction, 2/5. And the reason I like this method is because it works on pretty complex looking fractions. For example, let's say that I have 36 50-seconds. 36 50-seconds seems like it would be really difficult to simplify, but if I know my multiplication facts, it's actually really not that bad. Starting with the 52, I recognize that 52 must have a factor of 2 because it's an even number. So, factor of 2. And I can figure out pretty quickly that the other factor, 2 times what makes 52, is 26. So 52 is made up of a 2 and a 26. Similarly, 36 is made up of a 2 and an 18, and that's just a fact that I remember. I could break this down even further, but for now I'll eliminate my 2's because I see I have common 2's, common factors that can be eliminated. I can do that again now. I see that 18 and 26 are both even still, which means they must have 2 as a factor. 18 is 2 times 9, and 26 is 2 times 13. Again, eliminating those common 2's gets me to my simplest form, which is 9/13. Here's another one, 14 56. Now I could continue just thinking about things as being even if I wanted to, but in this case the first thing I notice is that 14 and 56 have a common factor. 56 is made up of 7 times 8, and 14 is made up of 7 times 2, which means that this common factor 7 can go away, which gets me to 2/8. Well, 2 and 8, again, have a common factor, which is 2. 2 is 2 times 1, and 8 is 2 times 4. If I eliminate that 2, I'm left with the simplest form, which is 1/4. So I really feel like identifying and eliminating common factors is the simplest way to simplify fractions. And as you've seen from these examples, you really don't have to do it in one giant chunk, identifying the greatest common factor. You can do it step by step. Equivalent fractions work the same way. An equivalent fraction is just a fraction that's equal to another fraction. So in these examples here, you might say that 14/56, 2/8, and 1/4 are all equivalent fractions. They all equal the same thing, just in different levels of simplification. Every fraction has an infinite number of equivalent fractions. Let's take, for example, the fraction 1/3. It's already in simplest form because there's no factors I can take out of it that would make a difference. However, I can always add factors back in. So just like I removed multiplied factors to simplify, if I want to unsimplify, I can get equivalent fractions that way. For example, let's say I decide to multiply in the factor 2 to both the top and the bottom. It's a common factor. I can put it in both, and what I'll end up with is an equivalent fraction to 1/3. And I could have picked any number, any factor that I wanted to multiply in. It would have gotten me an equivalent fraction. So I could take 2/6 and find another equivalent fraction. Let's say I multiply in 7 this time. That's going to give me the equivalent fraction 14/42. So in this example, 1/3, 2/6, and 14/42 are all equivalent fractions. Because I've started with the same simplified fraction and multiplied in additional factors in each scenario. There are two important qualities of equivalent fractions that's probably worth knowing. One is that when fractions are equivalent, they always reduce down to the same simplest form, which really makes sense because they're the same fraction to start with, so it makes sense that they reduce to the same simplest form. The other neat thing about equivalent fractions is that if I cross-multiply them, I end up with the same values. Let me show you what I mean. If I cross-multiply 1/3 and 2/6, which we know are equivalent fractions, 1 times 6 is 6, and 2 times 3 is 6. So I got the same value for both sides. Same thing, if I cross-multiply 2/6 and 14/42, 2 times 42 is 84, and 14 times 6 is also 84. So that's a neat quality of equivalent fractions. And it's a quality that we've been taking advantage of for quite a while. This is the reason cross-multiplying proportions works. We're basically solving for x and finding the value that makes an equivalent fraction. It's worth pointing out also that fractions, let's say 2/3 and 8/10, which are not equivalent to each other, don't have this quality. 8 times 3 makes 24, while 2 times 10 makes 20. They're not equivalent fractions, so when I cross-multiply them, they don't produce the same value. But the big thing here is that if you ever need to create an equivalent fraction for any reason, you can do that by taking the fraction and multiplying the numerator and the denominator by the same factor, and that'll always produce an equivalent fraction. And here are your practice problems for the lesson. It says this, but please make sure you look at the bag of marbles here on the right and use that for answering each of these questions, which are going to ask you some probabilities and some other things as well. Good luck.